Good day. Today we will continue the series of the videos that I'm starting with my last video about the equipment nozzle evaluation. And today we will evaluate the tank or cylindrical tank or bullet or pressure vessel, but today we will not using pressure vessel, or we can consider it as a pressure vessel, and how we will apply our calculation. Today, our standard will be the WRC297, which is used to calculate the local stresses on the nozzles or the equipment, and for the tronions and for any connection that attached to the pipe, the local stress which is created due to this connection. For this, we have two standards, the WRC 107 and the WRC 297. WRC 107 had been updated by the WRC 537. But it's the same methodology, same procedure, and same everything. The difference that the research paper that was based, that WRC 107 was based on it, already lost, and it was very old, so they just needed to refresh it and put a new charts and equations. That's it. This is the only difference between the 107 and the 537. Today I will use this equipment since I didn't find any old equipment I'm working, so I used one of the research paper that I was reading lately for on the pressure vessels, and I will use this dimension for it. Let's start. First of all, let me delete this and show you how we do it. We will go to the end. And create extension. Here will be okay. Okay. $260. And okay, this is the start of the nozzle of the tank here, and we will consider it 150 as a projection. After we have here this tank is diameter is 1600. So what we will do, 1600 divided 2, it's 800. So extends extra 800 with the same diameter of the nozzle, and we will put it a rigid element with 0 weight. We don't need to put any weight, so the Caesar will consider it 0. Okay, here if we consider this the nozzle, our nozzle, there's that we will consider 1300 from this saddle and to the nozzle, and the total between the two saddles is 5375 millimeters. So we will only model this piece. So we'll turn back to our model and let's do this, the 1300 to the saddle. sorry, and we will consider it a rigid element, and 100, and we need to consider here the saddle. It's total 1050 minus 800, so our saddle is 250. We need to consider 250 here, and we will put our strain. If we consider this saddle is the fixed saddle, usually any pressure vessel you will have one fixed saddle and the rest of the saddles is sliding. So we will consider here this is the fixed saddle. We will fix it by putting restraints or supports in the 3 direction. Okay, and don't forget here you don't have the saddle, so the program doesn't, or the Caesar does not know that there is a restraint in rotation. So we need to add here a restraint for rotation in the Z direction. Okay, and let's continue back. We have 5375. We already took 130, so 13. So we have 4075 in the minus direction. By the way, I forgot, we need from here to start considering the diameter of the vessel, which is 1600, and the thickness, not here, from here. Okay, and the thickness, which is 12. Okay, and we need to consider 0 tolerance because we don't have tolerance, and based on the equipment, if we have corrosion allowance, we will consider 3 millimeter corrosion allowance, and we use the same operational load case. And we go back here. By the way, let me make sure the same. Okay, so we'll go back to the rigid. Why we are considering the thickness and the diameter? To consider the stiffness while it is calculating the stiffness movement of the equipment. Okay, let's go back and put this as a rigid element also. After we have minus 800 as a rigid element, then minus 250. Here we will put a restraint. In the X direction. Okay. This saddle doesn't have the same temperature and pressure of the equipment. It will have an ambient temperature, so we need go downwards. This saddle is 40 to 50. This one need to adjust it to 21. Pressure, and we don't have even. Okay, after we need to put it back 150 here, 200 here, but we go back here to put it 2, 5, and 1. Okay, you can check this by putting temperature. Let's see. I think we have a problem mistake. We need to also check this temperature because sometimes it happens in mistakes. See, it's considering 150 while we are using 90. using 120 here. Try always to make this check, because this error, errors is commonly used after finishing your model. You need to make the check in temperature and check in pressures too. See, we have also here problem with the pressure. This commonly happen in modeling because of the extra data that you are entering, so it happens. So you need to always to check the before you finish the calculation to check this. Now go to put the stiffness. What we will do of the nozzle of the tank, we will go to nozzle flexibility. This time we will use the WRC297. We have here the axial on the Z direction, so we put it Z direction. Here we will consider the stiffnesses on the X and the saddles. So here to the head is 1350, and here 4075. It will be shown on the drawing of the equipment. Here 600, 1600, thickness 12. We don't have a pad thickness. Material, we can put the material if we have the material of the plate. I don't think we have a material of the plate since it's piping oriented. Okay. Now go to the load case. Insert our load case and then run the analysis. Here, after running the analysis, we need to check the nozzle load. So we just close the analysis. Go to the main page of the Caesar and use analysis tab and check WRC. Before that, we need to go to the result report, print the restraint summary, and go to the input and record the diameter of the nozzle to 19.075 and 8.1788, and the nozzle time. Okay, close it, go back to tab here, put it here. You can choose where you put your file and the units. Open this tab. It will be open for the WRC197, but now since we are using the vessel and we don't use the spherical or anything, we will use the 207. After I finish this, I will give you a comparison between the 107 and the 297. So we need to delete this and insert 127. Our design temperature is 120. Our design pressure is 5 bars. Vessel, and the outside diameter of the vessel is 1624. The thickness is 12. The corrosion allowance that we consider is 3. We don't have any material, any stress concentration factor, so we keep it 1. And the material that we are using is SA grade 70. We can choose whatever we need, but we will use the SA 516 grade 7. The nozzle attachment, the nozzle diameter is 219.075. Wall thickness is 8.1788. Corrosion allowance that we are using is 1, and we are using a 106 grade B. Okay, the loads. We need here, since we are using the ASME section 8, we need to consider here the induced pressure thrust and the stress indices. And also we need to put the loads, and this is why I was printing the restraint load summary. Our nozzle is this one, this one, so we need to put the maximum load. Okay, here we need to consider something. This is a vertical nozzle, so our axial load or the radial load in this case will be Fy. This is what I'm telling you about changing the global coordinates, which is this one, to the local coordinates, which is this one. So in our case, the local coordinates will be the Fy is the radial force, so we need to put the Fy here. Our circumferential force will be our circumferential force will be the Fx, and our circumferential force will be sorry, this is the circumference. This is our longitudinal force will be the Fz. Okay, our torsional force will be our torsional moment, sorry, will be the My, and our circumferential moment will be the one rotating around the body of the vessel, which is Mz, and the longitudinal moment will be the one that's coming on the body of the vessel. Okay, then telling to run the analysis. The analysis will give you the output. This is our input, and here we have a failure in the sustained load. We have a failure here. This is because we are running the indices. If we go back here and remove this one, the false, put it false, and rerun again, we found it passed. But still, we need to put it back. We're just deceiving the program, but based on the requirement of the version 2, we need to put this force back. So based on that, if we calculate it, we have a failure in the sustained load. So we need to somehow reduce the load on the nozzle to satisfy the premium load of the sustain. Okay, I told you I will go back and give a definition, a comparison between the 107 and 10. Okay, here's not this one. Yes, this one. The WRC107 and the 537 is mainly the oldest local stress code. It was used for spherical and cylindrical shell, while the WRC297 is only used for the cylindrical shell, so it's only used for the pressure vessels and the polyethylene, but this one can be applied for the pressure vessel head or a spherical tank. Here, the calculation was based on the unpenetrating shell, while here it's based on the open shell, which means this one can be used to calculate the trunnion, the local stress based on the trunnion, but WRC297 cannot be used. The WRC01 is used for the solid and the hollow, rounded or rectangle shapes. This is why we are using to calculate it for any attachments like the lug, like the trunnions, any attachment to the pipe. We can use the WRC07, but we cannot use the 297. Here we can use if the nozzle is perpendicular, tangential, or even angled nozzles, it can be used here. But the 297, it's only for the cylindrical perpendicular nozzle. What is the good in the 297 then? It's have more ratio for the diameter nozzle to the diameter of the tank. It have more ratio for the diameter of the nozzle to the thickness of the nozzle. It have bigger ratio for the diameter of the tank to the thickness of the tank. Okay, but this one can be, but 107 can used for the shell head nozzles, can be used for the spherical tanks, and can be used for any attachment like trunnions and lugs. But when we use a pressure vessel, we usually prefer the 297 because of the flexibility calculation of the nozzle and also the big ratios for the diameters to thickness. I hope that I explained how to perform the analysis for the WRC297 and how to input the flexibility for the nozzle. I hope this is clear, and if there is any question, please don't hesitate to ask me. I will appreciate it if you subscribe to my channel and open the bell to follow up this series of equipment nozzle, and wait for the rest of the videos where I will explain the pumps also. Thank you.